And once again, it's this paper from summer 2022. So anyone who's doing a GCSE chemistry paper in February, so that'll be people who are doing their double award, that exam is on the 22nd of February. I can't remember whenever the one in May time is, unfortunately, because I don't. I forgot to write it down, and CCEA blocks a lot of documents. Have blocked a lot of documents from being able to access in the US, so I don't actually have those written down. But anyone who that's relevant to, your school should be able to tell you, or you can look it up online. But the next chemistry exam, the ones who are doing the double award science, their science exam is on the 22nd of February 2024. But I'm going to get started now. Really sorry for the rambling there. Really sorry for being late. But I'm going to start this paper. So, same deal as last time, where we get all of our important information for this exam given to us at the bottom of that cover page. So that cover page, you put in your centre number. Your centre number is given to you by your school. It's school specific. Your school is your centre. And your candidate number is individual to you. If you go to, like, let's say if you went to a night class, you would have a different candidate number and a different centre number there than you would for your main school. So I have two different centre numbers and candidate numbers because I did school and then I did my chemistry and biology after the fact, and did those in a night school. So you'll have a centre number and a candidate number. Those will stay with you throughout your duration of doing your exams. You write those in the space provided. One of the big reasons that we use centre numbers and candidate numbers is for anonymity. So to keep who it is, just it's an extra layer of security. So it's for anonymity. You have a 5-digit centre number and a 4-digit candidate number. And then below that, we've got the information for candidates. So that'll be a lot more like your instructions are more about like what you do. That you have to answer all questions. Don't write in gel pen and answer all questions. So that will be specific to that exam. And then underneath is more information to do with the questions in particular. So we have a quality of written communication question for this paper. That's essentially our essay question for the paper. It is going to be worth 6 marks, so it's worth quite a lot. And it's going to be worth 6 marks, so it's worth quite a bit. And the one on this paper is to write up a particular practical about preparing a dry salt. So if you know that, you're doing well. Then in addition to that, we've got our data leaflet. So I have the data leaflet printed out for me. Looks like this. The one that you will get will be much larger. You get a data leaflet and it's an A3 periodic table, a cover sheet, and then on the back it's got some information about polyatomic ions. It has information about solubility and insolubility as well. Is there anything else on it I'm missing? Yeah. Polyatomic ions, so your negative and positive ions, and stuff about things that are soluble and insoluble. So it can be useful in certain exams. Some exams more so than others, but we are going to move on. And we're going to start the first question. So this first question, A1, some elements in the periodic table are shown below. Using only elements in the table above, answer the questions below. So I've noted that this question was answered really poorly, according to the examiner's report. The main reason why it was considered to have been answered incredibly poorly was a lot of people didn't read the specifics of each individual question, and we'll get into that a little bit more once we've actually done the question. But one of the things that's worth noting in this question is they've highlighted the word only. This means that they want to make it very clear they only want us to use hydrogen, sodium, potassium, copper, zinc, carbon, oxygen, neon, and argon. They don't want us to use any other elements. They don't want us to look at our periodic table and make up our own answers from that. They want us, from our knowledge, to only use information about these elements. So we've got a couple of metals here. We've got sodium, potassium, copper, and zinc. They're all metals. And we have 5 non-metals as well. Those are our hydrogen, our carbon, our oxygen, neon, and argon. And the first part of 1A then is name one element which forms an oxide, which is a colorless liquid at room temperature. So, the room temperature thing is quite important to note. So that means, like, what would you expect to be liquid at room temperature? So the stuff that's in my bottle would be liquid at room temperature. I've got tea in there. It's an iced tea. But they want us to name one element which forms an oxide. So they don't want us to say what the oxide is. They want us to name the element. So specifically, what element forms the oxide. So we want, from this list, to figure out which one. Something that bonds with oxygen that forms a liquid. So we can immediately get rid of neon and argon from our possible answers. The reason being, neon is a noble gas and argon is a noble gas. Noble gases do not react with don't react with anything else in the periodic table. They are inert. They're gases and they don't react with other things. So immediately it's not a liquid, and it's not it's not a liquid. It's not going to react to form an oxide. So we can get rid of that. If we look at carbon doesn't actually form a gas. Sorry, it doesn't form a liquid at room temperature. Carbon dioxide and carbon monoxides are both gases. If we look at our metals here, so our sodium oxide, potassium oxide, copper oxide, and zinc oxide, they would all be solids. So that leaves us with hydrogen. So when hydrogen bonds with oxygen, we get H2O, which is better known as water, which is going to make up most of the contents of my drinking water there. And that is going to be our answer, because that will have been a colorless liquid at room temperature. But the thing is, they don't want us to say water. They want us to say hydrogen. If it sounds like I'm rambling about that point, yes, I am. And there is a reason for it. The reason I'm rambling about this one point is that the hydrogen with the water forms the hydrogen with the oxygen forms water, but it says it wants us to name the element. And it is noted in the examiner's report that 1I was perhaps the least well answered question on the paper. A wide variety of incorrect answers were given, with a reasonable number giving sodium or the symbol rather than the required name. So basically, multiple people, instead of giving hydrogen, gave a wrong answer that would form a ionic salt, and gave the answer as the symbol from the periodic table in the question, instead of naming the element. They specifically wanted the name. So below then we've got one of the elements forms an oxide, which is a colorless gas at room temperature. Write the formula of that oxide. So we've actually already answered this whenever I was talking about the different whenever I was talking about the different things that could form an oxide earlier. And I said that you could get carbon dioxide or carbon monoxide, and both, if we look at the mark scheme for this paper, are accepted answers. So they've got CO2 or carbon monoxide as potential answers. Okay. So going back to the question paper then, we have then got write a formula of an ionic compound formed between two of the elements. So an ionic compound, we know, is a bond between a metal and a non-metal. So we can choose either hydrogen, carbon, oxygen, neon, or argon to bond with sodium, potassium, copper, or zinc, except we actually can't use the neon or argon because they are noble gases, they are inert, they don't work. So whenever it comes to writing formula then, where's my stylus? Whenever we get to writing formula, we have to be able to do swap and drop. So sodium is group 1 and oxygen is group 2. I just picked sodium and oxygen because it's an easy one to do. You will probably use oxygen regardless of which one you're using, because carbon's an awkward one to do your bonding with. And yeah, I mean, you could do hydrogen. You're welcome to do hydrogen if you want. But yeah, for ionics, you can really only use the carbon or the oxygen, and carbon's just awkward. So you'll be bonding one of your metals to your oxygen. So oxygen's group 6. Elements in group 6 have a valency of 2 because valency goes 1, 2, 3, 4, 3, 2, 1, 0. Valency is the amount of bonds something can form. So when we have covalent, it's shared bonds. Ionic, on the other hand, is you form 2 ions from the elements in the compound. So with our swap and drop, we end up with Na2O. So that is sodium oxide. So the thing about sodium oxide is you could have also done that for potassium. You would have gotten the same answer. It would be K2O. You could have done it with copper, but with copper you would have had an additional step. So the additional step for if you wanted to use copper as the thing for your as your chosen metal, you would have to go, and this applies to zinc as well, you would have had to have gone to your ions on the back of your data sheet and have used that then to find out what the valency is, because copper and zinc are transition metals, so you don't inherently know what their valency is. Okay, so moving on to part B. So part B is a question about metals. Potassium reacts with water. Potassium floats and moves on the surface. It melts to form a silver ball, burns with a flame, and eventually disappears, leaving a colourless solution. Apart from wearing safety glasses, state 2 safety precautions which should be taken when adding potassium to water. So, when we add potassium to water, there are a couple of things that we do. One is, as mentioned, we wear safety glasses, and that's because whenever we begin to react, something that is as reactive as potassium with water, it will be very aggressive and it can splash and can cause a lot of issues. It generates a lot of heat, so it can burn us. So to protect our eyes, we wear safety glasses. But we have to take another of additional steps on top of that. One of which is, it's great if I'm wearing safety glasses and a lab coat and protecting myself. However, if anyone's watching, there has to also additionally be a safety screen. So there has to be a protective barrier in the way. So the first answer that they would accept for this would be a safety screen. The second answer that they'd accept then is, when you're adding the potassium to the water, they would want you to use tweezers. They want you to pick it up with tweezers and drop it in. The reason for that is, again, it's to protect yourself, to protect your hands. It's like the potassium would be very reactive. So it's for safety. They would have you use safety tongs for that as well. Now, one of the things that was noted in the examiner's report about this question was that a lot of people answered it with generic lab safety techniques. For example, tying your hair back, or if they didn't have tying hair back, they had If it wasn't for things like tying hair back, it was maybe standing while doing the experiment. Very generic lab safety stuff, but they didn't want generic lab safety information for this question. They wanted it to be specific to the experiment. I'm of the opinion that that isn't particularly evident by the question, and you would have to infer that. So if you get a question like this, even if it doesn't say, what specific lab safety steps would have to be taken for this experiment, give ones that are relevant to the particular experiment at hand, not ones that are generic and should be followed at all times, such as standing when reacting things, or tying hair back, or wear a lab coat. It would use lab safety techniques that are specific to the experiment that you're doing, even when it doesn't say it in the question. In my opinion, that's a failure of the writing of the question, but we do what we do to make the examiners happy. So, explain why potassium floats on water. So this is to do with density, and it's told us to explain. So explain usually means give a good bit of detail. It can't be a one-word answer. They want a full sentence. So for potassium floating on water, the reason is it's less dense than water. So if you have, say, ice, and ice floating in water, ice is actually less dense because all of the molecules are further apart from each other, and so that's why it floats. So anything floating on water is just less dense than water itself. What actually, I need reminded. What's the okay? Yeah. So potassium is less dense than water. Explain why potassium melts during the reaction. Again, we're using the word explain here, so they're going to want a full sentence. They want you to not describe, they want you to elaborate on why it's the case. But it is only worth 1 mark, so we don't need to go into too much detail. And the answer is simply, the reaction is exothermic, which heats the potassium past its melting point. So when a reaction is exothermic, it is releasing energy between the bonds. So if it gives out heat, it's exothermic. Think exo, outside, exo like exoplanet. Thermic is then heat. Anything, thermometer is measuring heat. So anything with therm in it is to do with heat. Exo means outside heat. The endothermic, on the other hand, which is obviously the opposite of that. So whenever it takes in heat, whenever a reaction gets cold, that is making more bonds, and that the energy making is the energy is being taken into the bonds, and whenever that happens, it gets colder, and that's endothermic. Endo for inside, so endocrine, the endocrine system, which is your hormones, that will be like chemicals on the inside. So that is, that's how I remember the difference between exothermic and endothermic. So exothermic, it heats it up, brings the potassium to its melting point, the potassium melts. In addition to that, the potassium goes on fire. And whenever potassium is lit, so we have our ion flame tests, which is whenever you have your nichrome wire, you pick up a little bit of the salt and you put it in front of a Bunsen burner. You'll get a specific color, and you'll get the same color as you would in that test as you would when putting potassium on water, and the answer is lilac. So you get a lilac flame, and so you're very particular about the color that you use. You can't just say purple; you have to say lilac. It's a lilac flame for potassium. Okay, so then if we move on, we've got explain in terms of electrons why the reaction of sodium with water is less vigorous than the reaction of potassium with water. So I'm just going to go back up to part A of this question and take a look at the periodic table. So we have both potassium, which is K, and sodium, on this periodic table. So the sodium then is sodium is one period above the potassium. They're both in group 1, so they have the same number of electrons on the outside. So that's not our answer. Our answer isn't to do with the number of electrons in the outer shell. Instead, it's actually to do with the distance of the electrons from the central nucleus. So think of it like magnets. The further away one magnet gets from another magnet, assuming that you've got, like a north and a south magnet, the further away they get, the less likelihood that the easier it becomes to pull away one magnet from the other. If they're right beside each other, they might have a really strong attraction. But that attraction, that strength in the two magnets, gets less and less the further away one magnet is from the other. And it's very similar here. So the fact that in potassium you've got your outermost electrons are an extra layer out, it's a further distance away from it's then a further distance away from the nucleus, and therefore that attraction is reduced. So the outermost shell of potassium is further away from the nucleus than that of sodium, and the sodium therefore is more likely to keep its electron. The potassium is more, it's easier for potassium to lose an electron. So let's take a look at what the mark scheme says. So mark scheme says the outer electron in sodium is lost less readily, which means it's more likely to stay. It's just awkward wording there. The outer electron, that should be the outer electron of sodium, is closer to the nucleus, whereas the outer electron is more, it says more attracted. Yeah, the outer electron of sodium is more attracted to the nucleus. Now, alternatively, if you'd said the reverse, if you'd said that sodium loses it more readily because the outer electron is further away from the nucleus, then that would still count as a valid answer. Sometimes on the mark schemes they'll explicitly note that, sometimes they won't, but that would be an applicable answer here. Because it's relative. This answer is relating to is comparing sodium to the potassium, but you could do potassium to the sodium. So let's take a look at what the answer for that one, how that question was answered then. So 1B. 1BI was poorly answered. Safety screen was given a range of incorrect names, including the blast screen and plastic barrier, and general procedures which were not credited. So that's what I was saying earlier about general safety procedures. You should answer the question similarly to, with procedures that are specific to the experiment that you're talking about. Candidates needed the comparison to gain marks in B2. So B2. Oh yeah. So they needed to say that the sodium. No, sorry. They needed to say that the potassium was less dense than the water. So they had to have that full sentence. They couldn't just say one was less. You couldn't just say less dense or density. You had to say potassium is less dense than water. A small number referred to the gas being evolved as the reason for the potassium floating on water. I have no idea what that is talking about because I haven't seen any of those answers. Only the best performing candidates obtain the mark for why potassium melts during the reaction. Almost all candidates correctly gave lilac as the observed flame color. And for 5, a common error was failure to refer to the outer shell electron being lost or closer to the nucleus or more attracted to the nucleus. No marks were awarded if it was not clear the candidate was referring to the outer electron. Yeah, I think that's fair because it is the outer electron that is actually forming reactions. Anytime you're talking about reactions, anytime you're talking about reactions at GCSE level, it's almost always just the outer electrons you're dealing with. Okay, so down below, now we've got a more maths type question. So, many elements, including neon, exist as isotopes. What what is meant by the term isotopes? So, anytime you see iso in a word, it means same. So I deal a lot in my full-time job with isocenters, which are like the same point everything's rotating around. That's called an isocenter. So iso just means same. At A-level chemistry, people talk about things being isoelectric, which basically means has the same electronic configuration. So isotopes are the same element, but a different mass number. And there are two ways that you can actually, there are two ways you can talk about isotopes at GCSE level. You can say what I just said, which is same element, different mass number, or same atomic number, different mass number, or you can alternatively say same number of protons, different number of neutrons. You cannot chop and change between the two. You cannot say same atomic number, different number of neutrons. You have to say number and number, or nucleon and nucleon. Nucleon is a collective term for neutrons and protons. So you have to either do mass number and atomic number, or you have to do neutrons and protons. You can't chop and change between the two. So it is either the same atomic number and different mass number, or it is the same number of protons and a different number of neutrons. But that's what an isotope is, just different numbers of the same thing. A very common mistake I find with the understanding of isotopes is that, like, what we normally associate on the periodic table, for example, 1 hydrogen is not an isotope, like the normal isn't an isotope. It is. Your regular expected form of a chemical is just a regular isotope of the chemical. Every iteration is an isotope. You can just be talking about one type of isotope, and that isotope might have different properties, such as being radioactive, like in carbon-13 compared to carbon-12, which is stable. Okay, so now we have a percentage abundance of isotopes of neon are shown. Calculate the relative atomic mass of neon. Give your answer to one decimal place. So, how we go about this then is, firstly, relative atomic mass. So relative atomic mass is kind of like the weight we would guess one atom to have compared to another, atom of the same oh gosh, my brain has stopped. That's embarrassing. Relative atomic mass is like a guesstimate at how many nucleons a particular atom will have. So it's not an exact number. So we can have, as you can see here, 20 neon, 21 neon, and 22 neon, and all of those are isotopes. So our relative atomic mass is just the average number, and that's why, even though you can't have half a nucleon, you can have 0.5 in your relative atomic mass number. So I'm going to start this question off, and basically we have it's a weighted mean. So basically it means that if we have 90% of our 20 neons, if 90% is 20 neons, then that has to be weighted 90%. So that means our first, why is that not working? Oh, there we go, it's working now. So 90.1 times 20. So the weighting is including the percentage, essentially. Plus, I'm not going to have enough space for this. 21 times 0.3 plus 22 times 9/6. And then because it's an average, we divide that then by our total. And our total is 100 because it's a percentage. And that gives us 20.8 2 because it's asked us for the answer to 1 decimal place. And that's only worth 2 marks, despite the fact that there is a lot in this. Despite the fact that there's a lot in this bit up at the top, like that's a long equation, but it's only worth 2 marks because it's quite a simple equation. And one of those marks is going to be for giving your answer to the correct. One of those marks is going to be for giving your answer to the correct number of decimal places. So, calculate then is obviously anything that includes using an equation. And give is state. So they only wanted it to 1 decimal place. So therefore, they wanted it to 20.2. So if we take a look at the answer, yeah, they allow 1 mark if you answered with 20.195. So one of those marks was for getting the correct number of decimal places. So the meaning of the term isotope was widely known, and most candidates scored full marks in part AI. But it should be noted that incorrect initial terms such as molecule or compound are penalized. So I'm going to scroll up here. So at the top of each type of examiner's report, it gives a little bit of a generic explanation into how candidates did, rather than going into the detail of each individual question. And it does say here that terms like atoms, molecules, ions, particles, elements, compounds, etc. were not well known and were confused by these terms. So an atom is like one thing of an element. So that is all of its protons, neutrons, and electrons together. That is an atom. Overall, an atom has no charge. An ion, on the other hand, is almost the same, bar one thing. It does have an overall charge because it will have lost or gained electrons. That's the difference between an atom and an ion. A molecule is a little bit more complicated to explain. A molecule is one thing, essentially. So that could be a single atom. So for the example of neon, or for the example of neon or argon, the number of atoms and the number of molecules will actually be the same because there's no bonding there. But a molecule will be one of a thing. So a good example would be oxygen, where oxygen is a diatomic molecule, which means that it only exists in pairs. So you will have double the number of oxygen atoms in a sample of oxygen than you will have the number of molecules. So one molecule, and that's a compound because it has a chemical bond. So a compound are 2 or more atoms that share a chemical bond. Elements then will just be your list of things on the periodic table, and your particles are going to be the constituent parts of the atom. So your electrons, neutrons, and your neutrons, electrons, and protons. I thought I was going to say neutrons, electrons, and electrons. That's incorrect. Neutrons, electrons, and protons. Those are your particles. Those are the only 3 particles that you have to know and deal with. And that's how that works. That's what all of those different things are. They are confusing. They're worth remembering, though, because if you can get your head around those individual terms, you will have a much better understanding of your chemistry questions. And whenever you go to sit your chemistry exam, understanding those terms and spending less time trying to figure out what is meant by those terms will help you. And it will help you answer your questions quicker and have an easier time with trying to actually answer. It basically it'll allow for better time management in sitting an actual exam. So below then we've got the radius of a neon atom is 45,000 times larger than the radius of its nucleus. The nuclear radius is 3.5 by 10 to the minus 15 meters. Calculate the atomic radius in nanometers. So this is a tough question. In all honesty, it's a tough question. So we're gonna do this together. So I'm actually gonna move my paper. Okay, so what we want to do in this paper is we want to do 45,000. Okay, so that's the that's the magnitude and how the magnitude has increased times 3.5 by 10 to the minus 15. Okay, so that's what we want to do. And we're going to get an answer for that first. So that is going to be... where is it? Let's see. Yeah, so it's going to be 1.575 by 10 to the minus 10. And the reason that's not our overall answer is that is the answer in meters. So that would be worth 1 of our 2 marks for this question. And then what we need to do is divide this by the ratio for nanometers. So the way I always remember is, so meters are a bigger unit than nanometers. Nanometers are small, meters are big. So if you want a smaller unit, you need a bigger number. So 10 to the minus 10 is tiny. We want a bigger number. So minus 9, minus 8, minus 7, etc. Those are all bigger numbers because that the minus before indicates like a 0. So 0.003 is 10 to the minus 3. We want an answer that's not that. We want nanometers. So bigger unit, smaller number. Smaller unit, bigger number is how I always remember it. So therefore, it's going to be dividing by 1 by 10 to the minus 9. So if you're dividing, if you're dividing, you are making the number you're making the number bigger whenever it's a decimal place. So that gives us the answer of 0.1575 nanometers. I realize that's probably hard to read, but that's the best I can do. Okay. Didn't realize that was quite off screen. Yeah. Do you know what? I should maybe move my webcam. Let's see. That's there we go. That's probably better. That's probably better. That way it's not in the way of the question whenever we're looking at each individual question. Okay. Let's take a look then. I will scroll down. So this next question then, each row is worth a mark. So we have 5 rows and we have to fill in each of them. And for this question, the periodic table will probably, you'll probably find it helpful, but it will not be the be all and end all because we're looking in some cases at ions and stuff like that. So it's not as easy as it looks. So we're going to start, we'll take this first row. So we have hydrogen and we need to look at what the atomic number of hydrogen is. And normally we would give an answer of 1. Like if we just looked at our periodic table, it says that our hydrogen has an atomic number of 1. And that'll, that's true. It'll still be 1 for our atomic number because our atomic number doesn't change. Our atomic number definitionally makes that element that particular element. But the mass number on our periodic table is also 1. And that's 1. That'll be incorrect if we give it. And the reason for that is most hydrogens are like 1H hydrogen, which is also known as protium. You do not need to know that, but it's like protium is 1H hydrogen. But we have different isotopes of hydrogen. We have also got deuterium, which is 2 nucleons, and tritium, which is 3 nucleons. So 1 proton and 1 neutron is deuterium. 1 proton and 3 neutrons is tritium. but we have one neutron here, which means we've got a total of 2 nucleons. So our neutrons plus our protons give us our mass number. So the answer in here will be 2. So let's see. There we go. So we have an answer of 1 and 2. So that's why we need to read the information in the table carefully in order to fill it out. So below that then we've got our potassium. So potassium has an atomic number of 19. Okay, that's fine. Definitionally, that's what that should have. Okay, so 19. Our mass number then is 39. And to get our neutrons, we'll look at our protons first because that's the easy thing. So our atomic number and our protons are always going to be the same. So therefore, the number of protons is going to be 13. And it'll be the same for this one as well that's below it. So that'll be 13. Okay, so those are both, that's that filled out. So then to get our number of neutrons then, we do our mass number, because that's the total number of nucleons, take away the protons, which is 20. Okay, now that seems all well and good. That all seems fine. And then we have to fill in our electronic configuration. So potassium would normally be 2, 8. 8. I do not know why that did not come out looking like an 8. That looked like a 5. 2, 8, and 8. So then it would normally have a 1 on the end. However, we've got here, we can see that it's K plus. So, K plus rather than just K. Because of that, we know that it is an ion and not an atom, which means the number of electrons are going to be different. So here we've got 18 electrons because we've lost 1 electron. We've lost 1 electron because it's K plus. You minus the charge for the number of electrons. So we have 19 protons minus the charge, which is plus 1. So minus 1, 18 electrons. Okay, so below here then, well, let's figure out what element we've got below here. So if we look at our periodic table and we go along till we get to 13 as an answer for our atomic number, and we have aluminium. That my stylus isn't working. It's working again. Right, so aluminium. Okay. However, that's just the element. We don't know if it's an atom or an ion yet. We need to then look over here at our electronic configuration. And this says like 2 and 8, which would tell us 10 electrons. So we've got 13 protons and 10 electrons. So the way we figure out the charge is we do our protons minus our electrons, which would give us a charge of 3 plus. Really hard to see that's a 3, but it's 3 plus. So we can also sort of like ballpark that that's probably right because aluminium is in group 3, which means that it can lose 3 electrons to form bonds. And it's also a metal, so it will metals lose electrons, non-metals gain them typically. So then our mass number then. So our mass number is going to be the total of our neutrons and protons together, which will be 27. Okay, so now we're going to take a look underneath and to the one below it. So the one below it, I'm going to take a guess, is probably an atom and not an ion. The reason for that is it doesn't have a full outer shell. And if we take a look at the number of protons, we know that it's going to have an atomic number of 17, and the oxygen below is going to have an atomic number of 8 because the protons match the atomic number. And if we take a look at our periodic table and read across chlorine. So Cl has the atomic number 17. So this is a chlorine. The mass number then for the chlorine is going to be equal to the protons plus the neutrons. So we have 20 neutrons, 17 protons. And that gives us 37 for our total number of neutrons. Then finally, we take a look at our last row. Our last row is O with a 2- charge. So it's oxygen with a 2- charge. And our mass number is 18, and we've already said our atomic number and our number of protons is 8. So we have 10. So we have 18 minus 8 gives us 10. That does not look like a 1. I'm going to redraw that. Okay. Finally, then, we look at our electronic configuration. So because it's an ion, it probably has a full outer shell. So we're going to take a look at the number of, the group number of oxygen. So oxygen is in group 2, so it will probably have 2 full outer shells. If it was a metal and it lost electrons, it would have 1 less outer shell than the number of groups, but because it's a non-metal and has gained electrons, it will have the same. So 2 and 8, and 2 plus 8 gives us 10. That's 2 plus 8 gives us 10, and 8, so our number of protons, minus 10, which is our electrons, gives us minus 2, which is our overall charge. Okay, so that's all good. That would be worth 5 marks. There's quite a lot in that. That's a lot of effort for 5 marks, but some of those you need to be able to do really, really quickly. So your neutrons plus your protons give you your mass number really, really quickly. Your atomic number is the same as your number of protons, really, really quick. The ones that will take more time will be things like deciding whether or not something is an atom or an ion, and the charge on those, and then your electronic configuration. They're going to take more time than figuring out the number of protons and the atomic number. Then your mass number is also really quick. Is just going to be the neutrons plus the protons. So the next question, question 3, is salts. So it's this is under the topics of alkali, bases, and salts. This part of the paper then I think is the first bit of the paper that has like a question that wouldn't really be on the double award spec. So I need to keep that out. So this is the first one, and it's part 3 of A. Wouldn't be on the double award unit 1 spec. It is on the double award unit 2 spec. So we're going to look at, we have to name each of these substances. So substance A. So we've got potassium hydroxide plus hydrochloric acid gives us substance A plus water. So potassium hydroxide, hydroxides are alkalis, and our hydrochloric acid then is obviously an acid. It has acid in the name. So hydroxides take up hydrogens and acids give off hydrogens. So our hydroxide, which is OH, and our hydrogen, which is H, can form water. So we can see there that that's water. So we have to look at what's left behind. So potassium hydroxide, we've already said hydroxide is OH, so that's a potassium. And in hydrochloric acid, it's HCl, so it's potassium chloride. Potassium chloride is substance A. Substance B then, we've got it's plus nitric acid gives us copper nitrate, water, and carbon dioxide. When we have carbon dioxide in our generic equations, carbon dioxide and water as products, that's usually an indicator that we've reacted a carbonate. So whenever you react a carbonate with an acid, you get a salt, water, and carbon dioxide. So it's going to be some type of carbonate. So what we have to do is, we know that this nitrate has come from the nitric acid. So we have to look at what's attached to the nitrate, and it's copper. So we'll have copper carbonate as our answer for B. And then Z, zinc oxide plus something gives us zinc sulfate plus water. So oxides are alkalis. Acids and alkalis together give us a salt plus water. Zinc sulfate is a salt and water is water. So what do we get out? We get out, not what do we get out? What did we have to put in to get those out? So we had to put in some kind of acid. And I'm going to say we needed sulfuric acid. And the reason that is this sulfate has to come from somewhere. And we also had to have hydrogens in order to get our acid, our water. We needed hydrogens from acid to get our water. So in order for that to work, we then had to have sulfuric acid. So our answers are potassium chloride for substance A, copper carbonate for substance B, and sulfuric acid for substance C. So underneath we've got write the formula for copper 2 nitrate. So this is another one where you're going to have to take a look at your data sheet. But for once, we're not looking at the periodic table. And instead, this time we're looking at our ions in the back. And we look at nitrate, and we see that nitrate is... Where's nitrate? NO3. And it has a minus. So whenever you're doing swap and drop for a compound, you treat the charge as its valency. And then you also have copper too. So you can tell what the charge on a metal is going to be by the number beside it, basically. But if you look on your data sheet, it will also tell you that copper 2 is the answer for the valency of copper is going to be 2. So we have Cu, which is the 2, and our nitrate, which is NO3, and it has a valency of 1 because that's the charge on it. We do our swap and our drop. We end up with Cu, and then in brackets we put NO3, 2, because we need 2 of these nitrates attached to the copper. And that's how we do that. If we know that we're going to multiply a polyatomic ion, so those ions that are, this is nitrogen and oxygen, then we put those in brackets. So we end up with our answer being Cu NO3 2. And if we take a look at our answers, yep, Cu NO3 2. And if we take a look here at question 3, we have, where is it? The names of substances were correctly identified by most candidates. Part 2, the formula of copper nitrate was well known. Okay, so that was a question that was answered well. So people did know to include their brackets. That's good. Okay, so part B then, this is our... Oh no, wait, sorry. Part 3, I needed to tell you that one too. Sorry. Part 3, this is the part of the question that would actually only apply to people who are doing GCSE chemistry. This particular part of the question, this 1 marker, wouldn't apply as much to people who are doing GCSE or double award science. Well, it would, but only if they're doing Unit 2. It doesn't apply to Unit 1 double award science. And the answer is just water of crystallization is present. So there is water of crystallization if a salt is hydrated. So this is our essay question. And our essay questions are, are important to read. And typically I like to do them in terms of like identifying a step-by-step process for how to for how to do it. So my recommendation is always if it's describe a feature of something, is to just do step by step, just bullet point what all the facts are and then find a good order to write them in. However, that wouldn't work for this particular essay question, because this is a practical write-up. So describe how a pure dry sample of hydrated calcium chloride may be prepared from solid calcium carbonate and hydrochloric acid. In this question, you will be assessed on your written blah 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 blah. Okay, we know that. We've seen our essay questions before. We're going to take a look at the answers it was given and how they wanted the answer to be written. So, indicative content: place hydrochloric acid in a beaker or a conical flask. So we have that. We have a known amount of that, and then we add the calcium carbonate until excess. So we want more calcium carbonate added, in terms of like ratios. We want to add more calcium carbonate than needed. And we can tell that we don't need any more calcium carbonate by the fact that there will be no more gas given off. Then we filter that. We filter that solution so that we have basically that we get rid of our excess powder, our calcium carbonate. And then we heat the filtrate until its volume has reduced by half. Now, one of the things that was mentioned in the examiner's report was some people had said until the mass is half, but no, it's a matter of volume here. You want to give off. You want to boil off all of the water that was in it, and then you allow it to cool and crystallize. That's pretty simple. You just wait for it to dry, and then you filter off the crystals, and then you have to dry it again. So you realistically, it's easy to use low temperature oven or just between 2 sheets of filter paper. Some people would have it in like a specific dehydrator. So long as you've got this step in some shape or form. You can also say a desiccator, so that's something that absorbs moisture from the air. Any of those would work, really. So we look at this and we talk about this particular essay, and we'll talk about what people struggled with. So, question B part I was the quality of written communication salt preparation question, and this proved challenging for many candidates. Common errors included failure to add calcium carbonate in excess. So they were saying they would add the calcium carbonate. They didn't say how much calcium carbonate. You want more calcium carbonate than needed. Omission of the filtration step to remove the excess calcium carbonate. So that's why we filtered off. That's why we did our first filtration here in this answer. That first filtration is to get rid of the excess. Heating the filtrate to half mass, which is incorrect. We need to talk about volume. Those are two different things. Volume is the amount of space something takes up. Mass is related to weight. Mass is to do with how much is physically there. The two can be related by density, but they are two different things. And then we've got drying crystals with a paper towel. So, a small number used wrong reactants, even though they were given in the question. So that's just a reminder. Read the question carefully. Use what you're given. I often encourage people to use highlighters. Highlight things you think are going to help you. And this was part. Oh, that's related to the next part of the question. Okay, we can move on. But that's what was happening with the essay question there. So this is when you get a question like this where it is a write up how you would do something, think back to whenever you did it in your classroom and do step by step. If you have to explain what apparatus you would use, then do that. If that helps you, it probably will. and then, go step by step with how you do it. And if you want to include what reactions are happening, go ahead. So we've got write a balanced simple equation for the reaction between calcium carbonate and hydrochloric acid. So let's do that. Let's do that together. So we have got our calcium carbonate, which is CaCO3. Oh, I'm also going to give you a quick tip here. So we know that this is worth 3 marks. So you're going to get 1 answer for your having the correct reactants written, 1 mark for having the correct products written, and 1 mark for balancing correctly. If you see something that's only 2 marks, chances are there's no balancing needed. Always double check, but if it's 2 marks, you probably don't need to balance because you often have a 3rd mark for balancing. So then we're going to add hydrochloric acid, and I'm leaving a space between each of my compounds so that I can put in the ratios. H2O, I'm going to run out of space. H2O plus, I'm just going to do them below, CO2 plus CaCl2. Okay, so in this, I've got 1 calcium on both sides, so our calciums are fine. 1 carbon dioxide on both sides, so that's fine. 3 oxygens on both sides, 3 on the calcium carbonate, 1 on the oxygen, and 2 on the CO2, so 3 on our product side and 3 on our reactant side. But we only have 1 hydrogen and 1 chlorine on our reactant side, but we've got 2 hydrogens and 2 chlorines on our product side. So the easy fix for that is just add a 2. So now we've got 2 chlorines, 2 here, and 2 here, and 2 hydrogens, 2 on the hydrochloric acid, 2 hydrochloric acids, and 2 hydrogens in our water, and that's a balance. And it really is, in most questions, it's 2 marks if it doesn't require balancing, and 3 marks if it does require balancing. But I cannot stress enough, always double check just in case. So now we move on to question 4, which does put us more than halfway through the paper. I'll add one of the things that was mentioned in the examiner's report in regards to the previous question was to include lowercase letters. So the fact that you're dealing with carbon, which is just C, but you're also dealing with calcium, which is Ca, and chlorine, which is Cl, you need those lowercase letters to be able to understand which chemical you're dealing with at what time. Okay, so moving on. So 4A, I draw a dot and cross diagram to show how atoms of magnesium react with chlorine to form magnesium chloride, include the charges on the ions formed. So I'm just going to draw these. So sometimes you don't have to include all of the electrons, and sometimes you do. Because these atoms are quite small, it's easy enough just to include all the electrons. So I'm just going to do Mg. So Mg has, whenever it is atoms, it is partial outer shells. So we've got 2 on our innermost shell, 8 on the shells around it, and 2 on its outermost shell. I apologize for this being quite wonky, but yeah, that's what we've got. So then we've got chlorines, and please, whenever you're doing this, draw 2 chlorines out. It's just because on the laptop I don't really have enough space to do it, but in your exam, do 2 chlorines, please. So we've got dots for our chlorines, and it will be there 8 on that one, and 7 on our outermost one. So 1, 2, 3, 4, 5, 6, 7, 8. And we have 2 of those. Okay? And move that. Move slightly down here so I have more space. And we want to be MG. 2 there. 2 there. 2 there. And magnesium is a group 2 metal, which is why it has 2 electrons. Whenever it's an atom, it has 2 electrons on its outer shell. However, whenever it's ionized, it will lose those 2 electrons and have a 2+ charge. So we draw that, we have that 2+ on it. One of the things that was noted in the examiner's report was that the 2+ needed to be outside the atom to indicate that it was to do with the electrons. Don't put the 2+ beside the nucleus. That's just being pernickety. So then we have our chlorines, which we have 2 of. And each chlorine takes up 1 of those atoms. And I think whenever I was looking at the examiner's report for this, it had a typo on it where it said that people included the electrons from the magnesium on the chlorine when they shouldn't have. I was like, what it meant to say is that it didn't include them, but it should, because that's where it's getting them from. And I think it just forgot the word no somewhere. Times 2. And this will have a -1 charge. So we have 2 of those chlorine atoms, which will have a -1 charge. Whenever you're not using a wonky stylus on a laptop screen, draw both of them. Whenever you're doing them out by hand, draw both of your chlorine atoms, because they are, that's how they want the question answered. And we answer our questions the way the examiner wants it, because we have no room for argument whenever they're the ones with our papers. So yeah, draw both of them out. If we take a look, then so here we've got the magnesium with 3 shells, 2 on the outer shell, and then below 2 full shells, and the outer shell's gone, and overall it'll have a charge of Mg 2+. Oh, I forgot to write the electronic configurations below each of them. Actually, doesn't say to include them, so it's fine. And that the chlorine should be 288 with 1 cross on it. So if I look at the examiner's report, it has the typo on it. Most candidates scored at least 4 marks out of 6 for drawing the dot and cross diagrams. Question for formation of magnesium in part AI. Marks were lost for drawing the electrons lost by the magnesium in the outer shell of the chlorine atom. I feel like this was supposed to say marks were lost for not drawing the electrons, because quite clearly in the mark scheme they do have the electrons lost by the magnesium in the outer shell of the chlorine. So always be careful. Sometimes there are typos both in the mark schemes and in the examiner's report. It's very evident in the specimen papers in particular, because the specimen papers aren't sat by anyone, so sometimes the fact that there were fewer people looking over the mark scheme, there tend to be more typos in the specimen mark schemes than in the regular mark schemes. Anyway, we're going to move on to part 2. Bonding in magnesium chloride is ionic. What is meant by the term ionic bonding? So the electrons of a metal donate their electrons to a non-metal. Now oppositely charged ions experience attraction. So that's the answer I gave. However, that answer would not be credited, and there is a reason for that, and that is this 1 mark is for one very particular type of phrase that they wanted you to include. They wanted the term electrostatic forces to be included. So the fact that like the positive and the negative are attracted to each other. So Yeah, so attraction between oppositely charged ions via electrostatic forces. So it must include the attraction, like that electrostatic attraction. Okay, so part B then. This is a GCSE chemistry only part of the question. This is GCSE chemistry only bit for part B. So chlorine may react with nitrogen or ammonia to form nitrogen trichloride. Nitrogen, ammonia, chlorine are gases at room temperature. So our room temperature gases, that's more of a GCSE chemistry thing. It's not really in the double award science one. So I do not like the wording of this question, but we'll roll with it. So we'll start with the total number of electrons. We'll do each column. So total number of electrons in a molecule. So in a molecule of N2, there's no overall charge, so we don't need to worry about that. So our number of protons is going to equal our number of electrons. And we look at nitrogen. Nitrogen has 7. This is N2, so it'll be double that. So we will have 14 electrons overall. Then in our NH3, every hydrogen is going to have 1 electron, and our nitrogen has 7, so we'll have 10 in total because we have 3 nitrogens. My stylus is buggy. Okay, this is the total number of electrons in covalent bonds in one molecule. So electrons tend to be in pairs. So we have our lone pairs and our bonding pairs, and in Cl2, there are 2 electrons involved in the covalent bond because basically we only have 1 pair. It's 1 covalent bond between Cl2 because it has a valency of 1. Nitrogen, on the other hand, has a triple covalent bond because it has a valency of 3. And for every bond, there's a pair of electrons. So therefore, there are 6 electrons in that bond. And then the number of lone pairs in one molecule. So the number of lone pairs is going to be basically how many electrons on the outermost shells are not in the bond. So chlorine will have 8 electrons in its outermost shell, but it's sharing 2 of those. So therefore, we'll have 6 electrons, which will be 3 pairs, but we have 2 chlorines, so we have 6 pairs. Our nitrogen, on the other hand, it's a weird one. So the hydrogens will have 2 in their outermost shell, and they're all taken up in the bond. So the hydrogens don't actually contribute any. So the number of pairs is actually only 1, which is from the nitrogen. So the nitrogen has 2 electrons, but only 1 pair that is a lone pair, and the hydrogens don't have any pairs in the bonds. Write the formula for nitrogen trichloride. Well, that's pretty simple. It's just going to be NCl3. And that's shown to us by the fact that it's, nitrogen trichloride. Tri means 3. And it makes sense if you look at your swap and drop, because we've got 3 for nitrogen, 1 for Cl, swap and drop, NCl3. Okay, so explain why nitrogen is a gas at room temperature. So the answer, because the only intermolecular bond you deal with at GCSE level is van der Waals forces. So there are weak van der Waals forces between molecules which are easy to break. So you get 1 mark for stating that it's van der Waals and 1 for saying the van der Waals are easy to break. This question was considered to be a good discriminator question, and whenever we talk about good discriminator questions in exam terminology, what we mean is that what we mean by a good discriminator is it shows different levels of capability as well. So students who were good at explaining things, who were good at the exam, who knew their stuff, were able to answer this question, and students who couldn't. So it's very important to understand van der Waals and what van der Waals forces are. Something I'm going to add is each year a paper is sat teachers tend to get better and better at teaching the content because they will adjust based on things that people find most difficult on the questions. So one of the biology papers, one of the things that wasn't well known was that the cytoplasm was where reactions took place. But in years since then, teachers have made a bigger point in explaining that. So people now tend to know. Okay, so part C then. So chlorine also reacts with methane and with water. Do a dot and cross diagram to show the bondings of those things. So this means it's important for you to understand what methane is. Now, if you've done your organics already, so if you're saying resitting your unit 1, you actually might know methane quite well because it's in organics quite a lot. But methane has a chemical formula of CH4. So I'm only going to do the outer electrons for this. So our methane, so central at x dot x dot x. So I'm only doing outer electrons. This is a terrible drawing. I apologize. It's literally just I have so little room. Okay, so central carbon with 4 hydrogens, and each of those hydrogens are sharing one bond with a bond in the carbon, so that it has 4 hydrogen to carbon bonds. Water, on the other hand, is a bit easier. So we have H2O, so oxygen is in the middle and hydrogens are on the outside. So hydrogens in reality are smaller than oxygen. I am just genuinely so terrible at drawing on this laptop. So hydrogen has a formula of H2O. I can't draw H2O. So that's that's simple enough. I think a common mistake that was made according to the examiner's report was that the methane was written as NH4 plus. That is not methane, that is ammonia. And if you look at your polyatomic ions, you'll see that like ammonium is written as NH4 plus. Methane is chlorine H4. So then our water, on the other hand, H2O, I think there was a comment about it as well. I think some people were writing it as HO2 and they got their hydrogens mixed up. So that was 4C. 4C. Yeah, 4C. Surprisingly, dot and cross diagrams for methane and water and 4C were drawn incorrectly by many candidates. Ammonia was drawn by a few candidates instead of methane, and a small number drew water as HO2. So remember that oxygen is a central part of the molecule of water. So this question is like half and half for GCSE chemistry and double award. So the first part could be answered by someone who is doing the first part could be answered by someone who's doing double award. However, part 2 would be GCSE chemistry only. So we're asked what is meant by the term alloy, and basically this is just knowing your definition as is given by CCEA. So it's an alloy is a mixture of elements. So that's your first mark of the 3, at least one of which is a metal. That's your second. And the resulting mixture has metallic properties. So it's basically trying to enhance the materials of metal. That's the point of an alloy. That's why we use them. That's why we make them. And that first question would be applicable to both GCSE chemistry and double award chemistry. However, this next bit would be just GCSE chemistry. So different size molecules in a lattice prevent sliding. So essentially it's like an interlocking it's like an interlocking mechanism where the fact that the reason nichrome is harder than nickel is those different sized molecules kind of like lock together, almost like, so if they're all the same size, they're all the same level, they sit like that, they easily slide over each other. We know this because our metals are ductile and malleable, etc. However, when they're slightly different sizes, they sit more like this, where they're interlocking and they can't move around quite as well, and that makes a substance harder. Okay. So now we're back at our flame tests. So this is the second time that flame tests have kind of come up on this exam, because obviously we had lilac earlier for potassium. However, this is slightly different. We're dealing with different molecules here. So I thought I wrote down the answer incorrectly there. I was like, that's not right. My calcium, my A looked like a U, so it looked like I'd written copper. I was like, that's not brick red. Anyway, so these are just ones that you're either going to know or you're not. So our brick red ion in a metal ion test is going to be calcium. Calcium is brick red. My A's and my U's apparently looked similar, so I was looking at that and was like, copper's not brick red. Copper's blue. Copper's like a green blue, a teal color. It's not on it's not on this table, obviously. Lithium then. So what color do we get for lithium? We get crimson. So they're very similar. The lithium's kind of more pinky, kind of like a deeper red, whereas our brick red is it kind of shifts more orange. They're very similar. They're different, but you can't tell the difference, but they are very similar looking. And then our yellow orange then is sodium. Those are ones that you just have to know. If anyone knows a good mnemonic for remembering them, let me know. So part B then, this is our ionic equations. This is about precipitates and stuff. So this, you wouldn't be the hardest question in my opinion. However, people didn't do particularly well in this particular bit, which, what is a precipitate? A precipitate is basically a solid created when mixing two things together. I think in the so precipitate, a good example of precipitate would be if you're doing a metal displacement reaction, if a metal gets formed at the bottom, that's a precipitate because it's been formed from mixing two reactions together. Precipitates are usually insoluble if you can see them immediately. If you have to do some sort of filtration to get them, then they are soluble. But that's what a precipitate is. So now we're going to look at reactions, the reactions above, and state what color the precipitates formed are. So reactions 1. So we've got barium 2 plus and sulfate 2 minus. And the precipitate formed there is white. The vast majority of precipitates that form are going to be white. However, they're testing us here on some of the exceptions. So beneath then we've got reaction 2, which is iron nitrate and sodium hydroxide gives us iron hydroxide and our sodium nitrate. So the metal from the metal that's not on the hydroxide is usually the one that forms the precipitate. So the metal hydroxide we get out, which is our FeOH3, is going to be our precipitate. So whenever we have iron like that, that's very similar to rust. Like that chemically looks very similar to rust, where rust is are oxide. So you can kind of guess from that what kind of color you're going to get, and you're going to get brown because you're going to get something that looks like rust. Then we've got silver nitrate plus potassium iodide gives you silver iodide and potassium nitrate out. So for that one, basically silver nitrite is used as a chemical test for silver nitrate is used for a chemical test for the different halogens. So as you go down the halogen group, you get a slightly darker color. So you actually start with chlorine, and silver chloride will give you a white precipitate. Then below that, bromine will give you a cream precipitate, and then iodide will give you a yellow precipitate. And fluorine, which is at the top, it does not give you a precipitate. It will stay in solution. Rewrite equation 1 to include the state symbols. So I'm not going to rewrite it. I'm just going to write the state symbols above again in the actual question, because it says to rewrite it explicitly. Do that in the exam. Don't do what I'm doing. It's just I don't really have the space. So our barium salt. I said our barium salt. Our barium is going to be aqueous, which is AQ. Our sulfate is also going to be aqueous, and our barium salt is going to be solid. So our state symbols, we have 4 that we're concerned about at GCSE level. Those are our 3 basic states, which are gas, liquid, and solid. Our precipitate's always going to be a solid. We can physically see that it's a solid. Our gases are obviously also gas. So we've got oxygen, O2 is a gas. Anything that comes up, if it bubbles and it hisses, those are our gases. Hydrogen's a gas. CO2 is a gas. We have a lot of gases. Chlorine, Cl2 is also a gas. So we've quite a few gases that we just kind of have to know. You can kind of see where they are on the periodic table as well. I don't have a periodic table like visible on screen at the minute to be able to like identify it particularly well, but that's what our 3 main states are. But we also have aqueous. And what essentially aqueous means is dissolved in. So if something is dissolved, it is aqueous. Because it's been pulled apart, it is a different state. So our aqueous things will be the whenever we mix our solutions together, a lot of the stuff involved will be aqueous, but our precipitates are solid. Write an ionic equation for reaction 2. So that's a little bit harder. So our ionic equations, we do a couple of things for our ionic equations. I have to look up what it is first. There we go. So I need to be able to see this. So in our ionic equations, we do a few things. We look at something and ask whether or not it is ionic or not. So FeNO3 will be ionic. So I need to be able to see that equation. So FeNO3 is an ionic substance, so therefore it separates. So we will have Fe3 plus aqueous plus 3 NO3 minus, it is also aqueous. I do not have a lot of space for this. And then we've got our 3 Na plus 3 OH minuses. So, and then below, I've got on my reactants, this is awful, FeOH3, and that's a solid, plus 3 Na plus 3 OH minus. So that's all well and good. However, whenever we're writing ionic equations, so just to go over this again, because I meant to explain it while writing it and I didn't. In ionic equations, you separate ions into their positive and negative parts. So usually the metals are separated from the non-metals, or our acids, we will separate our hydrogens from them. However, we don't have any hydrogen-based acids here, so we don't have to worry about that. And we also only separate them if they're aqueous. So the fact that our FO3, like our basically our iron hydroxide, is our solid, we don't separate it. So I'm going to change color, get rid of anything that is the exact same on both sides. So our Na3 would be aqueous, our OH3 is aqueous, so same state and same number on both sides. We get rid of them. So we get, that was incorrect. I wrote something incorrect there. Sorry, that should be nitrate, this one. Sorry. Yeah, OH3 minus. So get rid of that and that. So we're left with our iron 3 plus our 3 OH minus gives us our iron hydroxide out. So I'm going to erase all of that so that I can write it in place. So on our ionic equations, we keep our charges and our state symbols. We just get rid of spectator ions, which are the ions that will be the same. They have the same number and the same charges on both sides. So, okay, there we go. So our final answer winds up being Fe3 plus Aq plus 3 OH minus gives us FeOH3, and it's a solid. Forgot to write my aqueous here, but that's our overall answer. So that's it. Like there's a good bit of work in ionic equations. So essentially you've got your marks for separating everything out correctly, both on the reactants and the product side, and then you've also got a mark for getting rid of your spectators. So your spectators are the ones that are the exact same both sides, same number, same charge. Okay, so then finally for this question we've got name the precipitate. So the precipitate involved in this reaction is, for reaction 3, is silver iodide. So you take the metal stays as it is. You look at the non-metal and see if it has, basically if it ends in an n sound, it becomes ide. So it becomes silver iodide. So it's silver iodide, not silver iodine. And now we're finally on the last question of this exam, which is going to be our this is our quantitative chemistry one. And some of these quantitative chemistry questions are actually pretty simple. So the main thing we are always concerned with whenever we're doing quantitative chemistry is N. Wait, I've done that wrong, sorry. So small n equals m over mr. So n is the number of moles, m is the mass in grams, and mr is the mr is the either the relative atomic mass or the relative formula mass of what we're dealing with. So calculate the number of moles of chromium 3 oxide present. So chromium, we take a look at our periodic table because we're not given it here. So chromium has a mass number of 52. So that'll be 104 because we have 2 of them. And we have oxygen, which has a mass number of 16, which would be 48 because we have 3 of them. So 50 plus 48 is 100. So our MR is going to be 100. Okay. And our mass, we have 1.9 kilograms. So kilograms is a bigger unit than grams, so we bigger unit, smaller number, smaller unit, bigger number. So we're going to a smaller unit, we want a bigger number, so we're going to be timesing it by 1,000. So that is basically 1900 divided by 1,000. Oh, sorry, I've done my maths wrong. I did 52 plus 48. It's 152. It's 152. Okay, so 152. So it's 1,900 divided by 152 gives us 12.5 moles. And that's our answer. It's really just a matter of plugging the numbers in and making sure your numbers are correct. So in this case, you needed to make sure that you were calculating the correct MR for your chromium oxide, and you needed to make sure that you were using grams instead of kilograms. So then we need to calculate the number of moles of magnesium present. So a common mistake that was done here, apparently, was people did they times the number of magnesium by 3, but you don't do that you don't do that. So we have just the number of moles of magnesium present are again, we're converting our kilograms to grams, so it's 1,200 grams divided by 24, which gives us 50 moles. Okay? So we need to state which one's the limiting reactant. So now that we know how many moles are present versus like the ratio, we go back up. So if I have 12.5 moles of chromium oxide, I would need 3 times that in I would need 3 times that in the number of magnesiums I have. So that would give me 37.5 moles. So I have more magnesium than 37.5. So therefore, this is the reactant in excess. We're looking for the limiting one. So the limiting one will be the one that's not in excess. So in this case, it will be our chromium oxide. Our chromium oxide will be the reactant in excess. So then we've got our next bit of the question. So calculate the mass of chromium formed. So we use our limiting reactant then to figure out how much chromium would be formed. So for every mole of chromium we put in, we get 2 moles out. So we will get 25 moles of chromium out. So N equals M divided by MR can be rearranged to get mass equals moles times MR. So our mass equals moles times MR then is going to be, the number of moles is 25 because it's 12.5 times the ratio, which is 2. So 25 times our RAM, our relative atomic mass for chromium, which is 52. So it's 25 times 52, which gives us 1,300 grams, which is 1.3 kilograms, which makes sense because you'll get basically whenever you're dealing with kilograms, you'd expect a number either in the high grams or in a similar number of kilograms, depending on the exact question you're dealing with. So this question then, part B, so 6B, is a Unit 2 question for double award, but it's Unit 1 for GCSE Chemistry. And we'll do this one. So this one's worth quite a few marks. It's worth 4 marks, whereas these ones up here are obviously worth like 1 or 2 each. In this question here, you would have gotten a mark for like your ratios and a mark for your calculation. So 10 grams of hydrated chromium nitrate was heated to constant mass, and 9.5 of anhydrous chromium 3 nitrate remained. So we're trying to figure out how much water is attached to each chromium. So essentially, we're looking at ratios again. So our first step here is we determine the mass of water. And the mass of our water we get from taking one away from the other. So it'll be 10 minus 5.95, which is equal to 4.05? Yeah, 4.05 grams. And then we're going to write what it is so we remember water. And then we figure out the moles of... Yeah, we're going to find out the moles of water. So, I need to change the battery in my pen. The moles of water then is going to be 4.05, and it will be divided by 18. The reason it's 18 is it's our mass divided by our relative formula mass. Oxygen is 16, hydrogen is 1, so 2 hydrogens and an oxygen, 18. So that gives us 0.225 moles. Okay? Then we find out our moles of chromium. Our moles of chromium is going to be 5.95, which were given in the question. That's our anhydrous amount. So that's the amount that's just the pure chromium nitrate. And it is divided by 238, which you would obviously have to work out as being the 52 chromium plus 3 nitrogens and 9 oxygens, which is a lot. That is a lot of that's a lot of numbers, but it's 238, and that will give you 0.025 moles. And x is going to be the ratio between the two, and x is always going to be a whole number, so you want to divide the bigger number by the smaller number. That's just the easy way to remember it. So 0.025 gives you 9. So x equals 9. And that's all there is to that. And you can follow those steps each time. So you want to work out your mass of water, your moles of water, moles of remaining salt, and then the ratio between the 2 moles. And then the only additional thing they can really throw in there to make that question harder would be to work out the mass of the, like if you measure it might give you the mass of the bowl and tell you the mass of the bowl, in which case you would also have to work out how much mass of your anhydrous salt you have as well. That's the only thing they can really do to make that harder. So yeah, and now we're back to something that applies to both Double Award Unit 1 and Chemistry Unit 1, or Double Award Chem Unit 1 and Chemistry Unit 1. So this is a decomposition, which is fine. We don't really have to understand too much about what decomposition is. We're just looking at how much we get out versus how much we get in. So calculate the loss in mass when 1.7 grams of potassium dichromate is heated to constant mass. So the mass that we lose is going to be the oxygen. Because everything else is still, everything else is still present as a solid. We're told that. So the only mass we're losing is the mass of the oxygen. So what we need to do is work out our we start by working out our moles of our potassium dichromate. So it is 1.47, and then I worked out earlier what the RFM of potassium dichromate was, which is 294, and then that gives us 0.005 moles. Okay, and then we get our moles of O2. So it's going to be moles of O2. It's going to be 0.005. So the moles of dichromate we had divided by 4 and times by 3, which gives us 0.00375. So the reason for that is you divide by what you have, you times by what you know, and that's how you can use the ratios quickly and just put them in like that. So that's how we get the moles of oxygen. So our mass loss then is obviously we rearrange our molar equation. So we get M equals N times MR. So it's 0.00375 times 32. And the reason we're timesing by 32 is oxygen is a diatomic molecule. So it's 2 oxygens. And we get 0.12 grams. So that's not a massive decrease in mass, but it's significant enough. So if we look at the equation, yeah, that's how they've worked out. And my answers are the same as what's given in the mark scheme. So now we're going to talk a little bit about what the examiner's report said about those equations. So, not about this question, about this question. So we didn't look at 5 or 6. We'll look at 5 and 6 now. So the description of the alloy was correctly given by most candidates in part A1. A2 proved to be a difficult question for most candidates. So that was explaining the fact that they couldn't side over each other because they're interlocked now because the atoms are different sizes. They failed to realize the presence of different size atoms meant the layers did not side over each other easily. Flame tests and colors and metals were well known. Very small candidates losing marks. Some did not follow the pattern of giving formula of the ion charge opposed to the name. Okay. So some candidates basically didn't write the ion as a formula. They wrote that they just straight up wrote what the name was. Yes, so I mentioned that the precipitate question was a good discriminator. Whilst most recognized precipitate was a solid, they failed to appreciate that it was when 2 solutions were mixed together. The precipitate colors were known by the majority of candidates. I'm actually pleasantly surprised by that. I thought most people would find that question quite hard. Common incorrect number to explain a common incorrect answer to explain the hydrogen hydroxide the iron hydroxide was orange. Only top performing candidates were able to rewrite the equation in the correct state symbols. And successfully write the ionic equation. So ionic equations in general are a type of question people find really hard, and they are worth practicing. You can get sheets for ionic equations online. I actually do recommend there is, if you can get someone to help you by telling you what state each of the reactants and products is, I would actually recommend the A-level, the AS questions book, just because it has lots and lots of example questions for doing ions in it, whereas in the GCSE question book there aren't that many, and beyond the fact that the A-level candidates have to immediately recognize what state a lot of the things are in, they're not really any harder. So I would recommend those. Part 6 then, AI were asked, AI and 2 candidates were asked to calculate the numbers. Magnesium, a substantial number of candidates failed to convert from kilograms to grams. So again, grams is what we use whenever we're calculating moles. We do not use kilograms. And if you want to go from a bigger unit to a smaller unit, you're going to have a smaller number to a bigger number. So the size of the number goes in the opposite direction of the size of the unit. Some candidates used MR of 72 for magnesium, but we only use 24 for magnesium because we don't use the big number when we're calculating moles. We only use the small numbers. The mass of chromium formed, calculated, blah blah blah. For part B, the degree of hydration calculation was completed correctly by most candidates. A common area was calculating the MR of chromium nitrate incorrectly. Okay. Yeah, so it's calculating MRs were a common issue for part B. And then many candidates chose an alternative method of calculating the mass of the salt instead of subtracting the initial mass, which is worth equal credit. A large number of candidates mistakenly calculated the mass of only one solid instead of the two. Answers typically gained partial credit. Again, incorrect MR values were used by a small number of candidates. So the maths questions were in general answered well. It was just small things that tripped people up. For example, using kilograms instead of grams, or if they were using this, then they only calculated the mass of one of the solids instead of two. If they were calculating the solids, it's faster just to calculate the gas, the mass of the gas. But yeah, that's us for today. That's us for that's us for the GCSE Chemistry Unit 1. I hope people find it helpful. This will be available online for people to view afterwards. I'll probably just get rid of the bit at the start. And if you are joining me tomorrow for the GCSE Physics paper, then that is going to be moved early. So I'm moving it to 4 o'clock. But that's all for today. Thank you very much. And I will see you